E darei la parola a Mark, il quale è uno scienziato molto, molto eclettico nelle sue passioni, direi non solo spaziali, anche terrestri, ama un po' gli estremi, non solo nel cosmo, ma anche sulla Terra, ama moltissimo indagare le profondità del mare, per esempio, oppure scalare le vette. Oggi ci occupiamo della vetta cosmica, per cui do a lui la parola.
I'd like to thank Giovanni for those very kind words. Let me just get this thing going here. So, this afternoon, I'm going to talk to you about the James Webb Space Telescope. And I started off here with just a summary of what we're going to say. So, I'm going to break the talk into three areas. The first one is, and I thank Giovanni here for suggesting this, trying to explain why this telescope is unique. Why is it different from all the other telescopes, both on space and on the ground? Then I'm going to talk about the science questions that we're building this telescope to address. And then finally, and I hope by this time you'll have realized just how challenging the technology is on this telescope, I'm going to talk about the technology and how the whole program is coming together. You've just heard an introduction, but I just wanted to say a couple of words about what I do. I'm basically the project scientist for the observatory of James Webb Space Telescope, and that means I'm kind of like a science policeman. I'm there to make sure that the telescope and the observatory in particular gets built and performs as we wrote the requirements for the telescope. So I'm there to make sure it actually does what we want it to do. Before I started working for NASA, as you heard, I worked at the Space Telescope Science Institute, and the big thing that I did there was I was a member of the Advanced Camera for Surveys team, and that was the last camera that was put on Hubble. So I really played a major role in building that camera, and in particular the sensors in the camera, pretty much the same as the ones you have in your digital cameras, but they were much bigger then, and digital cameras still haven't quite caught up with that size. But a lot of the wonderful pictures you see from Hubble, both today and in various places in bookshops and on the news, come from the advanced camera. I do research, and my research is in the formation and evolution of planetary systems, and in particular, trying to actually detect planetary systems and characterize them. So that's, in a nutshell, what I do. Now, you've already heard about James Webb, but it is very important. This telescope really is a change. Astronomers in NASA have been naming certainly NASA missions for some time after famous astronomers. So Hubble is named after Edwin Hubble. The Spitzer Space Telescope is named after Lyman Spitzer. And we also have an X-ray telescope named after a famous Indian astronomer called Chandra. The James Webb Space Telescope was named by Sean O'Keefe, who was then the NASA administrator. And he felt that James Webb had made such a contribution, not just to the Apollo program, which he presided over for most of its life, but also to space science. He really started space science at NASA. And I think this bullet here is really a testament to how his vision both got started and has endured. Just during his tenure, he flew 75 space science missions to look at the Earth and to look at space. That's a pretty amazing achievement, and we certainly, have a hard time flying that many these days as things have gotten more complicated and people wanted to do bigger things. So he really kick-started space science in America and at NASA, and I think, this is a fitting tribute to him that we name this telescope after him. Now, I want to this is kind of what we call in America an eye chart, but it does cover a number of very important things that I just wanted to say up front. So this is the James Webb Space Telescope, and I'll come back to talking about that in a minute. But what we call the mission lead, or the NASA center that runs this program, is the Goddard Space Flight Center, and I'm from the Goddard Space Flight Center. But James Webb Space Telescope is a big international collaboration, and we have major contributions that come from the European Space Agency, and the Europeans are providing a science instrument. They're making a significant contribution to another science instrument, and they are also providing the launcher for this, an Ariane 5 for this mission. We also have contributions from the Canadian Space Agency, and you'll see how all these contributions come together. But I wanted to emphasize, you're a part of this. This is, partly a European mission as well. And it really is important with these very large programs these days that we have international participation. It's just absolutely essential to make them work. The science instruments, in addition to coming from Europe, there's American contributions with the Europeans on this instrument here. And I'm going to come back and talk about these. We have one American instrument, and then the operations will be done by the same folks that run Hubble, the Space Telescope Science Institute, where I used to work. So that's all I'm going to say about that, but I just want to emphasize this is really a major international project. So why is JWST so unique, and indeed why is it different? I mean, you've already seen that it looks like probably no other telescope you've ever seen, and probably even something more akin to what you'd see on Star Trek. So let me just start off by highlighting some of the other facilities that astronomers have now, so you kind of understand what the context is for wanting to go to JWST. So the Hubble Space Telescope is a UV visible telescope, primarily designed to do UV spectroscopy and visible imaging in space. So it's above the atmosphere, and we don't have images being corrupted by the turbulence in the atmosphere. And we launched that in 1990. We repaired it at the end of 92. And it's been delivering absolutely outstanding science ever since, and has really changed the way we think. And we were to have had a launch next week for the final servicing mission to Hubble. And I actually only narrowly made it here, in fact, because I got called last Monday to go and sit on a Tiger team to assess the Hubble Space Telescope switch-on procedure. So Hubble had a problem last weekend, which basically caused it to do what's called safe, which is everything shuts down and it just sits there waiting for us to tell it what to do next. And we spent all week going over paperwork that dated back to the mid-'80s, making sure we understood what we were doing before we go ahead and switch it back on again. So it is getting to be an old facility, and it will be reinvigorated with this new set of instruments when we put them on. I think the plan now is that they'll go sometime next year, probably in the February timescale, and it will operate for something like another 5 years. Then we have the Spitzer Space Telescope, which is just at this point reaching the end of its formal operational lifetime. It's what's called an infrared imager, and I'm going to come back to why it's different from JWST in a minute. But it's going into what's called a warm phase, and that means that we've run out of liquid helium to keep it cold. So we're just running it now in a kind of a way that allows us to do science with the instruments which are least affected by not being so cold. So we get it as cold as we can, and then we just have to operate it in what we call the warm mission rather than the cold mission. And then, as you know, we have a lot of very large telescopes on the ground. So how are these different? Well, the major difference is that very large telescopes on the ground still have to look through the atmosphere. And as time goes by, we're developing lots of very new technologies that allow us to correct for the turbulence in real time. But there are some things that you can't correct for, and some wavelengths that you really can't do a good job of fixing up, even with these new technologies. And that's why we're going to this new telescope, and I'll show you why exactly in a minute. So the first thing that is very different is that the JWST is going to have a much larger mirror than Hubble, and a significantly larger mirror than Spitzer. So this is the Spitzer mirror here. It's a 0.8 meter diameter mirror, and it was that size basically because Spitzer is essentially a big fridge. And it was a trade between how much liquid helium they could carry and the size of the mirror. So that's what they ended up with. And Spitzer's done an absolutely fantastic job opening up a whole new region of astronomy that we hadn't thought much about. Hubble is over here. It's a 2.4 meter diameter mirror. And this just shows you the band passes. So this is the ultraviolet, the visible. This is the near infrared, which goes out to about 5 microns. And then from 5 microns out to 30, we call the mid-infrared, and then beyond 30 microns is really the far infrared. So JWST is being designed to go from basically the edge of the visible all the way through to 30 microns. And it, in that way, overlaps both the work that Spitzer has done and it will overlap some of the work that Hubble has done. But the significant difference is it has a much larger mirror. This is 6.5 meter diameter mirror, has 25 square meter collecting area. And what that means is it collects a lot more light. So it collects more light, and because it's a much larger mirror, it gives you sharper images. Now, we're designing this telescope to work in the infrared, and one of the problems with, well, it's not a problem, it's just a fact in optics that as you go to longer wavelengths, the sharpness of your images starts to degrade for a given size of mirror. So JWST's mirror will deliver the same quality of images in the infrared that Hubble delivers in the visible. And if you wanted to do better than that, you'd have to build something that was even bigger. And as you'll see, 6.5 meters is already, a challenge and will keep us busy trying to make it work. So the two reasons we are going to the bigger mirror are to collect more light and to get sharp images that we can use with the Hubble data that we have and with the ground-based data. And this image here just tells you why it's so important to collect a lot of light. So these are both Hubble images taken in the visible, and an HST orbit is about 45 minutes. So this is 13 of those 45-minute orbits, and it's a section taken from a survey called a deep field. And I've just highlighted a little box here, and this is the box after 13 orbits, and you can see all you really see is noise. It's like when you try to take a picture in low light levels with your digital camera and you don't have flash, you get a lot of noise and it's very grainy. As you collect more light, and in the way we did it with Hubble is by doing 400 of those orbits instead, you start to see a lot more features show up in the noise. The quicker way to do that is to have a bigger mirror, and then if you have a bigger mirror, you can push to that edge of your envelope much more effectively. Now, the reason we're going to the infrared is very simple, and I've just included a reminder of the electromagnetic diagram up here. And just for reference, I put what the sky looks like at different wavelengths. So this is what the sky looks like in gamma rays. This is how Chandra tells us it looks in X-ray. This is the UV sky, the visible. This is the infrared, and then we even push down into the microwave and the radio. And everywhere we look at a different wavelength of the sky, we discover different things. And what we want to do with the James Webb Space Telescope is look for heat emission, so really that infrared bandpass. And the reason we're doing that is because very distant objects are red-shifted, or their light is Doppler-shifted into the red. And you get to the point where that light's so Doppler-shifted, it's not in the visible anymore, it's all the way in the infrared. So if you still want to be able to see that light from these distant objects, you have to look in the infrared. And the more distant the object, the further into the infrared that light is shifted. And what we're actually looking at is UV and visible light. It's just that it shows up in the infrared because it's been Doppler shifted so far. And this figure here just illustrates that principle. If this was a nearby star, you see this is the spectrum and these are the key spectral features. As that star gets pushed away, if you make it more and more distant, you see these features start to get Doppler shifted to longer wavelengths. And this is a very distant object that's shifted these lines here by about 100 angstroms. We're looking at objects where the features are redshifted by thousands of angstroms. So that's why we're going to the infrared. Now, the infrared's really interesting, but one of the problems with the infrared is that if you're going to search for very faint objects, you need a very low background. Otherwise, you won't be able to see them. And one of the problems with doing infrared astronomy is that you have to start by getting your telescope cold. Because if your telescope's warm, all you're going to see is the light coming from your telescope, not the light that you're trying to image from very distant objects. So if we want to do this kind of astronomy, we need to get the telescope very cold. And in fact, we're going to cool JWST's optics to 40 Kelvin, which is 40 degrees above absolute zero. So it's extremely cold. And this figure here just illustrates this concept. So there's a red cup here, which has hot liquid, and the blue cup has cold liquid. And then this is a hairdryer. If you look at these in the infrared rather than the visible, you can see these images are basically scaled so that white is hot and darker colors are colder. You can see the hot liquid inside that plastic cup shows up as very bright emission, and the darker, colder liquid shows up as a sort of dark area. And again, this is the hairdryer. You can see the end of the nozzle is extremely hot, and then it's blowing out all this hot air. So if you want to look at faint objects, you do